Hi students, JEE main syllabus doesn't include solid state, but JEE Advanced does. By viewing these two videos, part 1 and part 2, you can learn the topics prescribed in the JEE Advanced syllabus for solid state. The videos also include many well-explained previous year questions and other model questions for JEE Advanced Examination. By the way, I am Dr. Suresh Matthew, a retired associate professor in chemistry. The purpose of my channel, Chemistry Master, is to upload video classes on chemistry topics related to NEET, JEE Main and Advanced, and other similar examinations. If you like the video, please subscribe my channel and forward to others. In part 2, we study about different types of defects or imperfections observed in crystal structure. Towards the end of this video, we will discuss multiple choice type, numerical type, matching type and a paragraph type previous year questions and model questions for JEE Advanced Examination. Let us study what is meant by imperfections in solids. As seen earlier, in crystalline solid, the constituent particles are close packed, leaving minimum vacant space. We can observe perfectly ordered arrangement of constituent particles in crystalline solids. Any deviation from perfectly ordered arrangement of particles in crystal give rise to crystal defects or imperfections. For simplicity of explanation, the constituent particles are assumed to be hard spheres which generates a three-dimensional structure. Ideally, a crystal consists of perfectly periodic array of atoms or ions. However, deviations may occur. The term imperfection or defect is used to describe any deviation from such ordered array. Point defects. These are deviations from a periodic arrangement that is localized to the vicinity of several atoms. This is a perfectly ordered arrangement. Now, a constituent is missing from this position, and that generates a defect. Then second type is line defect. That is the irregular arrangement of lattice points in a row. In the first row, the lattice points or constituent are arranged in a perfectly ordered manner. But in the second row, the distance between neighboring constituents are different. That is, dislocation in the arrangement of row occurs. Crystal defects can be classified in the following way. One is point defect and the other is line defect. Point defects are further classified into stoichiometric defects, impurity defects, and non-stoichiometric defects. Stoichiometric defects are further classified into vacancy defect, interstitial defect, Frankel defect, and Schottky defect. Non-stoichiometric defects are further classified into metal excess defect and a metal deficiency defect. We need to study only point defects. First, let us consider the stoichiometric defects. These defects do not disturb the stoichiometry or composition of the solid, also called intrinsic or thermodynamic defect. There are two types of stoichiometric defects: vacancy defect and interstitial defect. These types of defect occur in ionic as well as in non-ionic solids. Stoichiometric defects that occur in ionic solids are called Schottky defect and a Frankel defect. First one is vacancy defect. This type of defect decreases the density of the substance. Also occur when a substance is heated. This is a perfectly ordered arrangement of constituents. Suppose that A and B atoms are there. A, B, C, A, B, B, A, etc. Suppose that one A atom is missing. Therefore, another B atom should also be missing. So missing A atoms and B atoms are equal so that the stoichiometry remains the same. Because of these vacancies, the density of the substance decreases. Second type is interstitial defect. It increases the density of the crystal. So a perfectly ordered arrangement. These positions are called interstices. Suppose an additional A atom is present in one of the interstices. To maintain the stoichiometry, another B atom should also be present in the interstices. Since additional atoms come to the crystal lattice, the density of this crystal increases. Vacancy defects that occur in ionic compounds is Shorty defect and Frankel defect. And let us see what is meant by Shorty defect. So it is a vacancy defect shown by ionic solids. It is a stoichiometric defect. So this is a perfectly ionic crystal. And suppose that a cation is missing. Now the anion must be removed from the position. The number of missing cations and anions are equal to maintain the electrical neutrality. In sodium chloride, there are about 10 raised to 6 Shorty pairs. Shorty pair means vacancies due to Na plus and Cl minus per centimeter cube of the crystal at a room temperature. The defect decreases the density of the solid because of these vacancies. Mainly shown by ionic solids in which the size of the cation and anion are almost similar and have high coordination number. Few examples are sodium chloride, potassium chloride, cesium chloride, potassium bromide, silver bromide, etc. The second type of stoichiometric defect that is observed in ionic solid is Frankel defect. And this is an ionic solid, a perfectly ordered arrangement. And suppose that a cation is shifting into the interstices. The smaller ion, usually cation, is dislocated from its normal site to interstitial sites. Does not change the density of the solid, because even if a vacancy is created here and that cation is present here. Shown by ionic substances where there is large difference in size of the anions. Only smaller cations can shift to the shift to the interstices. Stability of crystal decreases, but conductivity increases. Some examples are zinc sulfide, silver chloride, silver bromide, silver iodide, etc. Silver bromide mainly shows Frankel defect, but shows Shorty defect also. Second category of defect is impurity defect. An impurity defect occurs when foreign atoms or ions are present as impurity in the lattice site. Example, if molten sodium chloride containing some amount of strontium chloride is crystallized, some of the sites of sodium ions are occupied by strontium ions. Strontium ions have plus 2 charge, and while sodium is having only plus 1. So one strontium ion will replace 2 sodium ions. Another example is silver chloride containing cadmium chloride. Impurity defect can affect the conductivity, color, and reactivity of a crystal. Presence of impurities can control electrical conductivity of semiconductors, which are essential for electronic devices. The defects that we have discussed so far do not disturb the stoichiometry of the crystalline substance. These are of two types, one metal excess defect and two metal deficiency defect. Those defects in crystal which leads to change in composition of solids are called non-stoichiometric defects. They contain constituent elements in non-stoichiometric ratio due to defects in their crystal structure. For example, Fe 0.930 and nickel 0.940. First, let us consider the metal excess defect. And metal excess defect are of two types. One is the metal excess defect due to anionic vacancies. So this is a sodium chloride crystal. Suppose that this crystal is heated in an atmosphere of sodium vapor. Now some of these sodium atoms get deposited on the surface of the sodium chloride crystal. Now a chloride ion now migrates to the surface of the crystal and combines with sodium to form sodium chloride molecule. Now the electron released from the sodium atom moves to the vacancy of the chloride ion and occupy there. Such defects are shown by alkali metal halides like sodium chloride and potassium chloride. The electron released from the atom, sodium atom, diffuse in the crystal and occupy the anionic site. These sites are called F centers. This is known as F center. F centers are responsible for the color of the crystal. These electrons are free and the electron in the F center can absorb visible light and get excited. For NaCl, the color imparted will be yellow. Excess lithium makes lithium chloride crystal pink and excess potassium makes potassium chloride crystals violet or lilac. The second type of metal excess defect is metal excess defect due to extra cation. So this is a perfectly ordered arrangement. It's an anionic crystal. And suppose that a cation is shifted into a cation is present in the interstitial position. So this is an additional cation. So in order to equalize the charge, an electron will be trapped nearby or in a nearby position of the cation. Therefore the crystal remains neutral. An example is when zinc oxide is heated, oxygen is released and zinc 2 plus ions and 2 electrons are produced. This reaction. The excess zinc ions move to the interstitial sites and the electrons to the neighboring interstitial sites. Because of the excess zinc ions, the formula becomes Zn1 plus X and X is the extra zinc ions produced. Zinc oxide, Zn1 plus X oxygen. Zinc oxide is white in color at room temperature but turns yellow on heating because of this. The second type of non-stoichiometric defect is metal deficiency defect. So this is a perfectly ordered ionic crystal. Now suppose that a cation is missing. So this is the position of the cation. So in order to equalize the charge, a nearby cation acquires additional charge, additional positive charge. This defect occurs when the metal shows variable valency. Example, transition metal compounds such as ferrous oxide, ferrous sulfide, nickel oxide, etc. forms such defects. These metals are capable of showing variable valency. If the metal is capable of showing variable valency, then only it can increase the charge on the metal. FeO is mostly found with a composition of Fe 0.95 oxygen. In crystals of FeO, some Fe2 plus cations are missing and the loss of positive charge is made up by the presence of the required number of Fe3 plus ions. Such defects are usually shown by metals which exhibit variable valencies. In the case of ferrous oxide, Fe may vary from 0.93 to 0.96. We will now discuss some previous year questions and other model questions for JEE Advanced Examination. Multiple choice questions with only one option correct. Question 1. In a metal deficient oxide sample, Mx by 2O4. M and Y are metals. M is present in both the plus 2 and plus 3 oxidation state and Y is in the plus 3 oxidation state. If the fraction of M2 plus ions present in M is 1 by 3, the value of X is option 1 0.25, 0.33, 0.67 and 0.75. The number of M atoms is X, but M is present in both plus 2 and plus 3 oxidation state. Number of M atoms from the formula equals X, and the fraction of M2 plus ions is 1 by 3. So therefore, the fraction of M3 plus ions should be 2 by 3. Number of M2 plus ions is equal to X into 1 by 3. X is the number of M atoms in the formula, and that of M3 plus ion is 2 by 3 into X. Now the sum of oxidation states of all the elements must be 0. That is plus 2 into X by 3, that is M3 plus 3 into 2x by 3 plus 3 into 2 plus minus 2 into 4 equal to 0. So by solving we can find out X, and X is found to be 0.75. So this compound will be M 0.75 by 2O4. So the correct answer is the fourth option. Question number 2. The Shorty defect may involve all but one of the following statements. The incorrect statement is 1. Vacant cation is to anion sites in the ratio 1:2 in an MX2 lattice. A vacant cation and a vacant anion in MX lattice. Vacant cation is to anion site in the ratio 2:1 in an M2X lattice. Random vacancy lattice in any lattice. Random vacancy in any lattice. So here we consider the Shorty defect, and it is a stoichiometric defect. Shorty defect will not disturb the stoichiometry of the solid. If random vacancy occurs, it will not maintain the electrical neutrality of the crystal. So the wrong statement is option 4, that is the correct answer. Here the stoichiometry is, if there is one M vacancy, there should be 2 X vacancies. Here the vacancies are 1:1, here it should be 2:1. The Shorty defect is shown by one strongly ionic compound having high coordination number, compounds containing cation and anion of almost similar size, all of this. So the answer is all of this. Question number 4. Nickel oxide on analysis showed the molecular formula as nickel 0.980. What percentage of nickel is present as nickel ions? Option 1 96%, option 2 4%, 98% and 2%. From this formula it is clear that nickel oxide is non-stoichiometric. So the formula of the compound is Na98.98 oxygen. Suppose that we take 100 nickel oxide, and from this formula it must contain 98 nickel ions and 100 oxide ions. Nickel exists in nickel plus 2 and plus 3 oxidation states. Suppose the number of nickel 2 plus ions is equal to X. Then the number of nickel 3 plus ions must be 98 minus X. So the total number of nickel ions is 98. The nickel oxide molecule must be neutral. So therefore the charges on nickel 2 plus nickel 3 plus and oxygen must be 0. So therefore number of nickel 2 plus is, the charge on nickel 2 plus is plus 2, so plus 2 into X. And nickel 3 plus it is plus 3. The number of nickel 3 plus is 98 minus X. For oxygen it is minus 2 into 100. So if we take 100 nickel oxide, 100 oxide ions, this should be 0. And from this we can find out the value of X by solving this equation. So X is found by 94. X is the number of nickel 2 plus ions. So therefore nickel 2 plus is 94. Hence the nickel 3 plus ions must be 98 minus 94, and that is equal to 4. So therefore the percentage of nickel 3 plus is 4.08 or approximately 4%. So the second option must be the correct answer. Yes. Question number 5. What type of crystal defect is indicated in the following diagram? 1. Frangal defect, Shorty defect, interstitial defect, Frangal and Shorty defects. So from the figure it is clear that here there must be a positive ion, and this is the position for a negative ion, and now this one should be positive and this one should be negative. So equal number of positive and negative ions are missing. So this type of defect is Shorty defect. That is the correct answer. Question number 6. The appearance of color in solid alkali metal halides is generally due to a Shorty defect, to Frangal defect, interstitial defect, positions, and F centers. And this type of color is due to the presence of F centers. In solid alkali metal halides, the color is due to the presence of F centers, which is found as a defect in the crystal structure. And in F centers are actually anionic sites occupied by unpaired electrons. When light falls on the crystal, these unpaired electrons get excited by absorbing light radiations, and the color observed will be the complementary color of the absorbed radiation. So the correct answer is option 4. Question number 7. Cations are dislocated in interstitial sites in Shorty defect, Frangal defect, metal deficiency defect, vacancy defect. So in Frangal defect, the cations are shifted to the interstitial positions. The smaller ion, usually cation, is dislocated from its normal site to interstitial site in Frangal defect. So that is the correct answer. Question 8. Which of the following statements about the interstitial compound is incorrect? They are chemically reactive, they are much harder than pure metal, they have high melting point than the pure metal, they retain metallic conductivity. In interstitial compounds, small atoms like hydrogen, boron and carbon enter into the void sites of the metal lattice. They retain metallic conductivity and are chemically inert. So therefore, option 1 is the correct answer. This is an assertion reason type question. Given below are two statements. One is labeled as assertion A and the other is labeled as reason R. Assertion A. In a particular point defect, an ionic solid is electrically neutral, even if few of its cations are missing from the unit cell. Reason. In an ionic solid, Frangal defect arises due to dislocation of cation from its lattice site to interstitial site, maintaining overall electrical neutrality. In the light of above statements, choose the most appropriate answer from the option given below. 1. A is not correct but R is correct. Both A and R are correct, and R is the correct explanation of A. Both A and R are correct and R is not the correct explanation of A. A is correct but R is not correct. So in particular point defect, an ionic solid is electrically neutral even if few of its cations are missing from the unit cell. That is, a nearby cation will acquire a higher positive charge. So this assertion is correct. And a reason also correct. In an ionic solid, Frangal defect arises due to dislocation of cation from the lattice site to the interstitial site. But the reason is correct, but reason does not explain the assertion. So the third option is correct. Since cations are dislocated to interstitial sites, electrical neutrality is maintained in Frenkel defect. In metal deficiency defect also, the electrical neutrality is maintained where a nearby metal ion acquires a higher positive charge. Question number 10. The incorrect statement about the imperfections in solid is: Shorty defect decreases the density of the substance. Interstitial defect increases the density of the substance. Frenkel defect does not alter the density of the substance. Vacancy defect increases the density of the substance. And we know that when some of the lattices are vacant, the crystal is said to have vacancy defect. Definitely this will decrease the density of the substance. So therefore vacancy defect increases the density. This is wrong. That is the correct answer. Which one of the following will show both Frenkel and Shorty defects? Sodium chloride, silver bromide, chromium chloride, potassium chloride. And we know that silver bromide shows both Frenkel and Shorty defects. The radius ratio of silver bromide is intermediate. Hence it shows both Frenkel and Shorty defects. Shorty defect arises when both Ag plus and Br minus ions are absent from their lattice sites. They have comparable sizes. Now because of the high mobility of silver ions, they easily move into the interstitial site, leading to Frenkel defect. So option 2 is the correct answer. Question 12. Slight yellow color of sodium chloride crystal is due to vacancy defect, interstitial defect, metal excess defect, metal deficiency defect. So when alkali metal halides is heated in an atmosphere of metal vapor, metal atoms get deposited on the surface of the crystal. The halide ion diffuses to the surface, combined with the metal atom to form metal halide. This causes metal excess defect. The electron removed from metal atom on the surface diffuse into the crystal and occupy anionic site. The anionic site occupied by unpaired electron is called F-center. Such crystals show color due to excitation of electrons under visible light. Sodium chloride shows yellow, lithium chloride shows pink, potassium chloride shows lilac or violet. So the answer is metal excess defect. Question 13. If in a crystal lattice of a compound, each corner of a cube is occupied by sodium, each edge of the cube has oxygen, and center of the cube occupied by tungsten, the formula of the compound is Na2WO4, Na3WO3, NaWO3, Na2WO3. Each corner of the cube is occupied by sodium. The corner sodium atoms are shared by 8 unit cell. There are 8 corners, so 8 into 1 by 8, and it is equal to 1. 12 edges are there. Each edge atom is shared by 4 unit cell. So number of oxygen atoms is 12 into 1 by 4 equal to 3. Tungsten atoms are at the center. So therefore 1 atom. So the formula should be NaWO3. Option 3 is the correct answer. Question 14. Atoms of element B form HCP lattice and those of element A occupy 2/3 of the tetrahedral voids. The formula of the compound formed by A and B is A4B3, A3B4, A2B3 and A3B2. Here element B form the HCP lattice. Suppose the number of B atom is equal to n. Then the octahedral voids will be n and tetrahedral voids will be 2n. A atoms occupy 2/3 of the tetrahedral voids. So therefore A number of A atom is 2n into 2 by 3. That is 4n by 3. N is the number of B atoms. So the ratio A is to B is 4n by 3 is to n. That is 4n is to 3n, or A4B3. Option 1 is the correct answer. Question 15. A compound of A and B slices in hexagonal close packing with A occupying lattice point and B occupying 3/4 of tetrahedral voids. The simplest formula of the compound is AB, A2B3, AB2. The effective number of atoms in HCP is 6. Here the close packing is hexagonal close packing. Number of A atoms is 6. That is A occupying the lattice points and B in the tetrahedral voids. The number of tetrahedral void is 6 into 2 equal to 12. Number of B atoms must be 12 into 3 by 4 equal to 9. Therefore the formula is A6B9 or A2B3. So option 2 is the correct answer. Question number 16. An any compound has a unit cell constituting of A ions at the corners of a cube and B ions on the centers of the face of the cube. The empirical formula of the compound will be AB, A2B, AB3. The number of A ions in the unit cell will be 1 by 8 into 8. So the ionic compound has unit cell constituting of A ions at the corners. The number of B ions on the center of the faces of the cube. So each ion is shared by 2 unit cells, so it is equal to 3. Hence the formula is AB3. Option 3 is correct. Question 17. Total volume of atoms present in a face-centered cubic unit cell of metal is R is the atomic radius. 120 by 3, 24 by 3 pi r cube, 16 by 3 pi r cube. Effective number of atoms present in FCC unit cell is 4. Total volume of atoms, volume of one atom is 4 by 3 pi r cube into 4, that is 16 by 3 pi r cube. Fourth option is the correct answer. An assertion reason type question. Given below are two statements. One is labeled as assertion A and the other labeled as reason R. Assertion A. In close packing of spheres, a tetrahedral void is surrounded by 4 spheres, whereas in an octahedral void is surrounded by 6 spheres. Reason. A tetrahedral void has a tetrahedral shape, whereas an octahedral void has an octahedral shape. In light of the above statement, choose the most appropriate answer from the option given below. If A is not correct but R is correct, both A and R are correct, both A and R correct and R is not the correct explanation, etc. So in close packing of spheres, tetrahedral void is surrounded by 4 spheres, whereas an octahedral void is surrounded by 6 spheres, and that is the correct answer. So A is correct. A tetrahedral void has a tetrahedral shape, whereas an octahedral void has an octahedral shape, and that is the wrong answer. So the correct option is 4. The shape of the void is different from the tetrahedral void means when the centers of the surrounding spheres are joined, a tetrahedron results, and when centers of the spheres of surrounding octahedral voids are connected, an octahedron results. Next is multiple choice questions with 2 or more options correct. Copper has face-centered cubic crystal structure. Assume the atomic radius of copper be 128 picometer. Which of the following statement is or are correct? Atomic mass of copper 63 gram per mole. 1. The unit cell of copper has 4 copper atoms. The packing efficiency of copper crystal is 68. The length of the unit cell of copper is 362. The volume of unit cell of copper is 4.74 into 10 raised to minus 20 10 raised to minus 24 centimeter cube. Now take the first option. The unit cell of copper has 4 copper atoms. Since it is FCC, the effective number of atoms will be 4. So option 1 must be correct. Then option 2. For FCC, the packing efficiency is 74%. So this is not correct. The length of the unit cell of copper is 362. For an FCC unit cell, the edge length A is equal to 2 root 2r. Radius is given as 128 picometer. So 2 into 1.4 into 128, that is 362 picometer. Option 3 is correct. Then option 4, the volume of unit cell of copper is 4.74 into 10 raised to minus 24 centimeter cube. Volume of the unit cell is A cube. A is equal to 362 picometer or 3.62 into 10 raised to minus 8 centimeter cube, and that is 4.74 into 10 raised to minus 23 centimeter cube. So here it is 24. So option 4 is wrong. Question number 2. Which of the following statement or statements is or are not true about hexagonal close packing? 1. Coordination number is tall. It has 68% packing efficiency. Tetrahedraloids of second layer are covered by spheres of the third layer. In this arrangement, the spheres of the fourth layer are exactly aligned with those of the first layer. The coordination number is tall. Take the first option. Consider the middle atom of this layer. It touches 6 other atoms of the same layer and also 3 atoms on the layer below it. Now consider the next layer. So it touches these 3 also. Therefore, from the same layer there are 6, 3 from below and 3 from the upper layer. So total is 12. So this option is correct. So we have to choose incorrect options. So this is not the answer. It has 68 packing efficiency, 68%. SCP and CCP, the packing efficiency is 74%. So that is wrong. So that is an incorrect statement. Next, tetrahedral voids of the second layer are covered by spheres of the third layer. So this is the first layer. Now consider the middle atom, and the second layer comes in this way. 3 atoms of the second layer and the middle atom of the first layer forms a tetrahedral void. Now it is open in this direction. So when the third layer, that is a repetition of the first one, it covers, the middle atom covers the tetrahedral void. So option 3 is a correct statement. Then fourth one, in this arrangement, spheres of the fourth layer are exactly aligned with those of the first layer. Spheres of the fourth layer are exactly aligned with those of the first layer. So this is the first layer of atoms. Now the second layer, that is not aligned. This is the third layer. First and third layer are in an aligned position. Now the fourth layer, and that is not aligned with the first one. In this arrangement, the spheres of the fourth layer are exactly aligned with those of the first layer. So this statement is wrong. So the answers are option 2 and option 4. Question 3. An excess of potassium makes potassium chloride crystals appear violet or lilac in color since some of the anionic sites are occupied by unpaired electrons, some of the anionic sites are occupied by a pair of electrons, there are vacancies at some anionic sites, F centers are created which imparts color to the crystal. Some of the anionic sites are occupied by an unpaired electron, and such sites are called F centers, and F centers are responsible for the color of the compound. So this is the correct option. Some of the anionic sites are occupied by a pair of electrons. Only unpaired electrons occupy anionic sites, so that is wrong. There are vacancies at some anionic sites. These anionic sites are occupied by unpaired electrons, so therefore they may not be vacant. F centers are created which imparts color to the crystal. That also is correct. So option 1 and 4 are correct. Question number 4. Which of the following is or are not true about the voids formed in three-dimensional hexagonal close-packed structure? 1. A tetrahedral void is formed when a sphere of the second layer is present above triangular void in the first layer. All the triangular voids are not covered by the spheres of the second layer. Tetrahedral voids are formed when the triangular void in the second layer lie above the triangular voids in the first layer and the triangular shape of these voids do not overlap. Tetrahedral voids are formed when the triangular voids in the second layer exactly overlap with similar voids in the first layer. A tetrahedral void is formed when the sphere of the second layer is present above the triangular void in the first layer. So this is the first layer. These voids are known as triangular voids. This also is a triangular void. This also is a triangular void. When we place the second layer atom fits to this void. So in this way. So a triangular void of the first layer. Now an atom from the second layer, this form a tetrahedral void. So a tetrahedral void is formed when sphere of the second layer is present above the triangular void of the first layer. So this statement is correct. So that is not the answer. Now all the triangular voids are not covered by the sphere of the second layer. These are the triangular voids. All these are triangular voids. When we place the second layer, only some of the triangular voids are covered, but these are not covered. These are not covered, that give rise to octahedral voids. So all the triangular voids are not covered by the spheres of the second layer. So it is a correct option. So we need incorrect options. 3. Tetrahedral voids are formed when the triangular voids in the second layer lie above the triangular voids in the first layer and the triangular shape of these voids do not overlap. So this is the first layer. These are the triangular voids. Now the second layer comes and some of the triangular voids are not covered. And these form tetrahedral voids. So this is the tetrahedral void. Now a triangular void in the first layer. So this is the triangle. And now this one, if we take these three atoms, that form another layer. So the triangular void, the triangle of this one. But this generates an octahedral void, not a tetrahedral void. So therefore this statement is wrong. So that is an incorrect statement. Now option number 4. Octahedral voids are formed when the triangular voids in the second layer exactly overlap with similar voids in the first layer. These are the triangular void of the first layer, that is the red triangle, and the triangular void of the second layer, that is a green triangle, and that do not overlap. They do not overlap. So therefore, option 4 is an incorrect option, incorrect statement. So the answers are option 3 and option 4. Question 5. The incorrect statements regarding defects in solids are: Frankel defect is usually favored by very small differences in size of cation and anion. Frankel defect is a dislocation defect. Trapping of proton in the lattice leads to the formation of F centers. Shorty defect has no effect on physical properties of solids. So we have to choose the incorrect statement. Frankel defect is usually favored by a very small difference in size of cation and anion, and that is wrong. So it is a wrong statement. Cation should be smaller. Frankel defect is a dislocation defect. That is correct. Cation slips into the interstices. Trapping a proton in lattice leads to formation of F centers. F centers are formed by trapping electron, not proton. So that is a wrong statement. Then Shorty defect has no effect on physical properties of the solid. Shorty defect decreases the density of the solid. Which is or are the incorrect statement or statements? Density decreases in case of crystal with a Shorty defect. Sodium chloride is insulator, silicon is semiconductor, silver is conductor, quartz is piezoelectric crystal. Frankel defect is favored in those ionic compounds in which sizes of cation and anion are almost equal. FeO0.98 has non-stoichiometric metal deficiency defect. 1. The density decreases in case of crystals with a Shorty defect, and that is correct. So we need the incorrect statement. Sodium chloride solid is insulator, silicon is semiconductor, silver is conductor, quartz is piezoelectric. That statement is correct. Frankel defect is favored in those ionic compounds in which sizes of cation and anion are almost equal. So Frankel defect is shown by ionic compounds with a large difference in cation and anion sizes. So that is a wrong statement. FeO0.98 has non-stoichiometric metal deficiency defect. Here it is metal excess defect. Oxygen is less. So that also is a wrong statement. So the answers are option 3 and option 4. Find answer to the following questions which will be a non-negative integer. Question 1. If the length of the side of the cube is 500 picometer, the distance between the body-centered atom and one corner atom in the cube in picometer will be. The distance between corner atom and body-centered atom will be half of the body diagonal. So body diagonal is root 3a. And therefore the required answer is root 3a by 2. That is 1.732 into 500 by 2, that is 433 picometer. Second question. Copper crystallizes in FCC lattice with a unit cell length of 362 picometer. The radius of copper atom in picometer is. For FCC arrangement, radius of the atom is a by 2 root 2. Radius of copper atom will be 362 by 2 into 1.414, and that is 128 picometer. Third question. A metal has FCC lattice. The edge length of the unit cell is 404 picometer. The density of the metal is 2.72 gram per centimeter cube. The molar mass of metal in gram per mole is. Avogadro constant is 6.02 into 10 raised to 23 per mole. Crystal has FCC lattice, so effective number of atom Z is equal to 4. Edge length A is 404 picometer, that is 4.04 into 10 raised to minus 8 centimeter. Density is given 2.72 gram per centimeter cube. Density is Zm by A cube Na. So M is equal to dA cube Na by Z, and upon simplification you get 27. Question 4. The radius of sodium atom in picometer if sodium metal crystallizes in BCC lattice with a cell edge length A equal to 430 picometer. In BCC lattice, atoms along the body diagonal touches. So this is the body diagonal. Atoms at the corners and the center. So therefore, atoms in the body diagonal touches each other. Body diagonal is root 3a. It consists of 4 radii. 2 radii, then one more, 4 radii. Body diagonal in BCC is root 3a. And this body diagonal can be divided into 4 radii. So therefore 4r is equal to root 3a. Hence root 3a by 4 is equal to 186.2. Therefore radius of the sodium atom is 186.2 picometer. Question 5. The density of solid argon is 1.65 gram per centimeter cube at 40 Kelvin. If the argon atom is assumed to be a sphere of radius 154 picometer, what percent of solid argon is apparently empty space? Molar mass of argon is 40 gram per mole. Radius of argon sphere is given, and that is 154 picometer, 1.54 into 10 raised to minus 8 centimeter. Therefore, volume of one argon atom is 4 by 3 pi r cube. 4 by 3 into 3.14, 1.54 into 10 raised to minus 8 the whole cube. And that is 1.53 into 10 raised to minus 3 minus 23 centimeter cube. Therefore, volume of all the atoms in 1.65 gram of argon. So 1.65 divided by 40, that is the number of moles, into Avogadro constant, that is the number of argon atoms. So into volume of one argon atom. So therefore it is 0.38 centimeter cube. Given that the density of solid argon is 1.6 gram per centimeter cube. That is 1 centimeter cube contain 1.65 gram of argon, which has a volume of 0.38 centimeter cube. Therefore, empty space equals 1 minus 0.38, that is 0.62 centimeter cube. Percentage of empty space is equal to 62. Composition of a sample of wurtzite is Fe.931. What percentage of iron is present in the form of Fe3+? Fe.931 is a non-stoichiometric compound and may contain Fe2+ and Fe3+ ions. If we take 100 Fe of ferrous oxide molecule, it will contain 93 ferrous ion and 100 oxide ions. 93 iron ions and 100 oxide ions. Let the number of Fe2+ ions will be X. Then the number of Fe3+ ions will be 93 minus X. For electrical neutrality, the sum of the positive and negative charges should be 0. That is plus 2 into 6, that is ferrous ion, plus 3 into 93 minus X, plus minus 2 into 100 is equal to 0. So from this, X is equal to 79. Number of ferrous ion Fe2+ ions is equal to X. That is X, so it is number of ferrous ions is 79. Number of Fe3+ ion is, here it is 93. 93 minus 79 is 14. Percentage of Fe3+ ions. Number of iron ions is 93. 14 is ferric ion, that is equal to 15.05. If sodium chloride is doped with 10 raised to minus 3 mole percent of strontium chloride, the concentration of cation vacancies produced per mole will be. When sodium chloride is doped with 10 raised to minus 3 mole percent of strontium chloride, there will be 10 raised to minus 3 mole of strontium chloride in 100 mole of sodium chloride. Therefore, the number of moles of strontium chloride in 1 mole of sodium chloride will be 10 raised to minus 3 by 100, and that is equal to 10 raised to minus 5. Since the charge on strontium ion is plus 2, it replaces 2 sodium ions to maintain electrical neutrality. Therefore, each strontium ion generates 1 cation vacancy. Hence, the number of cation vacancies will be 10 raised to minus 5, same as the number of strontium ions. Thus, the cation vacancies per mole equals 10 raised to minus 5 into 6.02 into 10 raised to 23, which equals 6.02 into 10 raised to 18. In a crystalline solid having formula XY2O4, oxide ions are arranged in cubic close-packed lattice, while cations X are present in tetrahedral voids and cations Y are present in octahedral voids. The percentage of tetrahedral voids occupied by X is. The lattice is formed by oxide ions, and it is given that it is cubic close-packed, or it is FCC lattice. So the effective number of oxide ions in the unit will be 4. Therefore, the number of tetrahedral voids will be double that is equal to 8. And number of octahedral voids will be same as that, 4. From the formula, X is to Y is to oxygen, that is 1 is to 2 is to 4. Since the number of oxide ion is 4, the number of X ions must be 1. Therefore, the percentage of tetrahedral voids occupied equals 1 by 8 into 100, that is 12.5. Now consider some matching type questions. Question 1. Match the defects given in column 1 with the statements given in column 2. Column 1, symbol vacancy defect, symbol interstitial fungal short t. Column 2, options 1, 2, 3, 4. Column 1, symbol vacancy type, symbol vacancy defect, shown by non-ionic solids, and the density of the solid decreases. So we can connect 1 to C. Second one is symbol interstitial defect. So shown by ionic solid density, interstitial density increases. So shown by non-ionic solid and increases density of the solid. So 2 with A. Then fungal defect, and a fungal defect is shown by ionic solids, and a fungal defect density of the solid remain the same. Similarly, Shorty defect decreases the density of the solid. Therefore, the correct option is option 2. Question 2. Match the type of unit cell given in column 1 with features given in column 2. Column 1, primitive cubic unit cell, body centered, face centered, and column 2 give the features. Then option 1, option 2, option 3, and option 4. Primitive cubic unit cell. Number of atoms per unit cell is 1. So in primitive unit cell, lattice points are present only at corners. One more option in column 2 could be connected to this. Each of the 3 perpendicular edges compulsorily have the same edge length. Since it is cubic, A is equal to B is equal to C. So 1 corresponds to C also. Then body centered cubic unit cell. Here also it is cubic, so we can relate it to C. Then In addition to contribution from corner atoms, number of atoms present in a unit cell is 1. That is from the lattice point that is present at the middle of the unit cell. So we can connect to D. Then face-centered cubic unit cell. Since it is cubic, we can also connect it to C. Then in addition to contribution from corner atoms, number of atoms present in the unit cell is 3. That is from the face centers. So 3 to E. Then for end-centered orthorhombic unit cell. And in end-centered orthorhombic unit cell, each of the 3 perpendicular edges compulsory must have different edge length. A not equal to B, not equal to C. So 4 connect to A. It can also connect it to this one. In addition to contribution from corner atoms, the number of atoms present in unit cell is 1. So in end-centered unit cell, there are 2 lattice points at the opposite ends. Each are shared by 2 unit cell. So the contribution is half plus half 1. So 4 can be connected to D also. So the correct option must be 1B, C, 2C, D, 3CE, 4A and D. So option 3 is the correct answer. Impurity defect is due to the presence of a foreign substance and sodium chloride with a strontium ions and some cationic site vacant. So 1 can be connected to C. Then metal excess defect, that is sodium chloride with the ionic sites called F-centers. And these F-centers are created by evaporation of some of the anions to the surface of the crystal. It generates excess amount of sodium ions. So it is a metal excess defect. Then metal deficiency defect. And this is ferrous oxide with Fe3+. Ferrous oxide with Fe3+ must be a non-stoichiometric compound. So therefore, this shows metal deficiency defect. So we can connect it to B. And this defect occurs when metal shows variable valency. Here iron shows Fe2+ and Fe3+. So this can be connected to D also. So the correct answer will be 1 to C, 3 to A, 2 to A, 3 to BD. So option 4 is the correct answer. Question number 4. Match the type of close packing given in column 1 with a statement given in column 2. Column 1, square close packing in 2 dimensions, triangular voids, hexagonal close packing, etc. Then option 1, option 2, option 3 and option 4. First one, square close packing in 2 dimensions. Square close packing in 2 dimension means the coordination number should be 4. That means in 2 dimension an atom touches 4 of its neighbors. Then hexagonal close packing in 2 dimensions. Hexagonal close packing in 2 dimension generates triangular voids. Then hexagonal close packing in 3 dimensions. Pattern of sphere is repeated in alternate layers, that is AB type arrangement. So 3 can be connected to D. Then cubic close packing in 3 dimensions. Pattern of sphere is repeated in every 4th layer, that is ABCA. So 4 to B. So the correct option may be option 1. Next, match the items given in column 1 with that of column 2. Column 1, non-polar molecular solids, unit cell parameters A, B, 4 Bravais lattices, 2-dimensional rectangular lattice, etc. Then option 1, option 2, option 3, option 4. Column 1, non-polar molecular solids. Non-polar molecular solids show the weakest attractive force, so therefore we can say constituents bound by London forces. So 1 can be connected to D. Then unit cell parameters A not equal to B gamma 90 degree. And there are only 3 parameters, so it should be, this unit cell must be a 2-dimensional unit cell. So we can connect it to the C, 2-dimensional rectangular centered unit cell or 2-dimensional rectangular lattice. Both have same parameters. So we can connect 2 to A as well as 2 to C. Then 4 Bravais lattices, and that is for orthorhombic system. So only 1 remain. Unit cell parameters A equal to BC, alpha equal beta equal gamma not equal to 90 degree, and that is rhombohedral system. So the correct option may be option 2. Next we shall consider paragraph questions. The following paragraph is for questions 1, 2 and 3. In an hexagonal system of crystals, a frequently encountered arrangement of atoms is described as a hexagonal prism. Here the top and bottom of the cell are regular hexagons and 3 atoms are sandwiched in between them. A space-filling model of this structure called hexagonal close packing HCP is constituted of a sphere on a flat surface surrounded in the same plane by 6 identical spheres as closely as possible. 3 spheres are then placed over the first layer so that they touch each other and represent the second layer. Finally, the second layer is covered with the third layer, and that is identical to the bottom layer in relative positions. Assume radius of every sphere be r. Answer the following questions. Question 1. The number of atoms in this HCP unit cell is 1, 4, 6, 12, 7. So this is an HCP arrangement, A layer, B layer, A layer. This middle atom is shared by 2 unit cells, so the portion to this unit cell will be half. These are corner atoms. The corner atoms are shared by 6 unit cells, and there are 6 corner atoms, therefore 1 by 6 into 6 is equal to 1. The atoms in B layer are totally inside the unit cell, so it is 3. Similar is the case with the bottom layer, half and 1. So the total number of effective number of atoms is 6. So the correct option is this one. The volume of this unit cell is 24 into square root of 2 r cube, 16 into square root of r cube, 12 into then 64 by 3 root 3 r cube. So this is the hexagonal prism or the unit cell, and we have to find out the volume of this HCP structure. The volume will be base area into height, and base area there are 6 equilateral triangles, 1, 2, 3, 4, 5, 6. So this is one equilateral triangle, and if we multiply the area of an equilateral triangle by 6, you get the base area. And the side of the equilateral triangle will be A, that is the 2 atoms here, they touch each other, so it will be 2r. That means area of equilateral triangle is root 3 by 4 a square. or root 3 by 4 into 2r the whole square into 6. This is the area of the base of the prism. Now the height of the unit cell is given as h is equal to 4r into square root of 2 by 3. By some trigonometric calculations we can find this. Let us see. So this is the hexagonal prism, that is a unit cell for HCP, close packing. Now I separate one unit cell, this is one unit cell actually, from this. Now if I place the atoms closely spaced, you will get this one. Now this is a unit cell in hexagonal close packing, there is a middle atom here. Now we consider this red line, it passes through the center of this transparent, I made it transparent, so this transparent green atom. Now I remove this part and I enlarge it. So this is the this corner atom and this is the middle atom, and this distance, that is AB, and this is the hexagonal system. This angle is 120 degree, so that is alpha beta is 90, gamma 120, and here this angle will be 120 degree. This is hexagonal system, that is primitive, and this is hexagonal close packing unit cell. So this angle will be 120, half of this will be 60. So this angle will be 60, this also will be 60. So therefore this red line bisect this angle, so this angle is 30 degree. Let this distance be D. Now cos theta is equal to r by d, and this distance is the radius of this sphere up to this point. Actually it matches with this one, this line. So r cos theta is equal to r by d. So d is equal to r by cos theta, that is 2r by root 3. Now from triangle, it is a right angle triangle ABC, 2r square is equal to d square plus h by 2 square. This is half of the distance of this unit cell, so this distance is h by 2. So that is 2r the whole square is equal to d square plus h by 2 the whole square, that is 2r square is equal to this one. So h square by 4 is equal to 8r square by 3, and from this x square is equal to 16 into 2r square by 3. Now h is equal to 4r into square root of 2 by 3. That is height of the unit cell h is equal to 4r into square root of 2 by 3. Therefore the volume of the HCP structure is equal to, this is the area of the equilateral triangle, into 6 into height. So that is 2 by 3 into 24 into 2 r cube. So option 1 is the correct answer. Then third question is the empty space in this unit cell. 74, 47, 32, 26. Now we have to calculate the packing fraction, volume of atoms in one unit divided by volume of the unit cell, and the effective number of atoms is 6. So therefore 4 by 3 pi r cube, that is volume of a sphere. There are 6 spheres, so this is the volume of the atoms of sphere in the unit cell, and 24 into square root of 2 r cube is the volume of the unit cell. So this is 0.74, or it is 74%. And here we have to calculate the empty space. So empty space will be 26%. So option 4 is the correct answer.